This is a video presentation which is created on base of, say, version 1 presentation which was done at LabVIEW Advanced User Group meeting in Copenhagen, 21st of March 2014. In this presentation, I will speak about dynamically assembled architecture in LabVIEW, of course. I will speak about problem of flexibility in architecture of programs, test systems, simulation systems, about desirable solutions, about object-oriented solutions, give you simplest UML diagram. We'll speak about main subject, dynamic assembling, provide simplest examples in LabVIEW, and give some discussion, mainly based on feedback from this meeting. The whole talk is about by reference object-oriented programming in LabVIEW, but of course general ideas are applicable to any other language, and some people would probably implement it with native LabVIEW classes which are not by reference in their nature. So for beginning, for those who are not so familiar with object-oriented programming in LabVIEW, I do one slide crash course in object-oriented programming. In object-oriented programming, we create a structure of classes, and classes are assembled as a hierarchical tree. We have parent class and children classes. In this case, we have parent, son, and daughter. All classes have some methods, or VIs. The methods have the same name, and in this case, in simplest example, it is a name do something. So parent can do something, daughter can do something, and son can do something. But of course they can do different things. Now we take a simple piece of code, parent, daughter, and son, and they can be assembled in the same array. Can be assembled because of all of them belong to the same hierarchical structure. What is the type of this array? Type of this array is parent. Both of them are in hierarchy of parent. They are subclasses to parent. So age, son, and daughter, when we speak about biological example, they carry genes of parents. But parents don't carry genes of children. So in this case, son and daughter can do the same things as parents, but they can probably do something else. Now, we take array, index it, and call method do. Because of type of this array is parent, method do is presented in our block diagram, but it doesn't mean the code of this method is executed. If we take index 0, first member in our array, we have code of parent method do executed. And in our case, in this code, it belongs to parent. It will show dialog, simply dialog with title dialog. Now we take index daughter, and with exactly the same code, but daughter's method do will be executed, and the result of execution will be completely different. Daughter likes to play music, at least B. Now, son, it's teenager, he doesn't do any work, he just lay on the sofa. Now we come to more specific things for our subject. It is a problem of flexibility when we create a test system. Let's take as example a car manufacturer who ask us to create a test system for work with assembly of different units in the car. And what is actually the car? Car is some number of units like wheels, like steering wheel, engine, or more generally saying a motor, and of course some advanced central processor. All modern cars have central processors. What we must do, we must create a test system which will communicate with each unit, which will test them, send commands, monitor their functioning, and so on. And of course, beside of communications with our test systems, our units communicate with each other in one way, like steering wheel, or in two ways, like central processor and motor and so on. So far so good. We create a lot of such systems. What is the problem with flexibility here? So far there is no problem. But tomorrow our manufacturer want to create some new variety, offer some choice for customers. And they say, we develop now completely new concept of wheels. We develop light wheels. And of course, light wheels are tested, controlled in different ways. So we have to create two different pieces of code for these two type of units in the same framework of the same car. Of course, it's just one more piece of code. We can some fix here and do some choice between two different type of wheels. But our manufacturer like to offer good service to customers, and they, for example, want to go to new developing markets and offer cheap version of wheels. After that, they say, okay, but we can offer different variety of steering wheels. Steering wheel like joystick for sport version of our car, and of course a helm for marine version of our car. Finally, everybody worry about environmental problems, and manufacturer develops completely new environmentally friendly engine. So as a result, we have very high variety of units in our system, and we have to communicate with each of them in own style. We have to collect completely different data. For example, if we have a joystick like steering wheel, like this racing wheel, we have two ways of communications. While normal wheels or more traditional wheels, let's say, they don't have any back communication, only from wheel to the system. What is the solution? Solution is interchangeable classes. Each unit in our system is described by a class. And when we start our system, objects of corresponding classes are created and objects are replaceable. So we have a class wheels, and we have many different versions of this class which can replace each other in the same framework. Now, UML diagram, how such system is designed class-wise. We have a test system is as a class, and we have this layer of abstraction. Abstract wheels, central processor, it's only one class. All processors are the same for all, maybe for all cars on the world, or similar at least. Steering wheel, abstract motor. And for each abstract class, parent class, we implement subclasses, some specific implementations. So in this case, conventional wheels, light wheels, cheap wheels, and so on. So all specificity is implemented in subclasses. All common things for wheels, all common things for steering wheel are implemented at level of abstract class. How does it work when we start the program? First, we read any file, or of course some more advanced source of initialization information, and create instances of different subclasses, specific classes. We know in this particular configuration we have light wheels, helm, and combustion engine, for example. And we create these objects, but we keep them as just wheels, just steering wheel, just motor, not like specific references, but we cast them to higher abstraction level, because wheels are always wheels. Helm is always a steering wheel, but not vice versa, of course. So, and we keep them here in test system. We have references to wheels, to general class. It doesn't matter which of them is implemented in this particular configuration. What is important here? That test system has wheels. All specificity is implemented in subclass. Now, the main process starts, and objects communicate with each other. They communicate with the system, but they communicate at level of abstraction of abstract classes at this level. So combustion engine has no idea which type of wheels is used. Steering wheel has no idea about other objects. So they communicate. Steering wheel communicates with wheels. motor with steering wheel, and so on. And everything what is specific is at bottom more specific abstraction level. But there is a more advanced, let's say, problem in our system. It is flexibility in relationships. What happens if manufacturer didn't get wheels from supplier and say us, we need to test our other units. We cannot wait until wheels arrive. So we create some kind of simulator. But even in this case, the system of relationship is changed. Instead of direct relationship between the processor and the wheels, we have to send some kind of minimum signals which just keep the system alive. But the changes can be more dramatic. What happens if central processor is absent? As a result, in really flexible system, we have to be able to reconfigure our system from the units which are available. So, see how many different relationships we can have here. And all these relationships must be configurable when we start our system. The solution is flexible architecture. Wish list. As a wish list, we would like to create a graph-like program. Each node in this graph represents some kind of unit. Each edge in this graph is direction of communication. Inclusion of a node, inclusion of an edge in this graph must be done when we start the system, according to initialization information. And the only limitation here, what we can and allow to apply to our system, is that there are no two-directional edges. If we need two-directional communications, we do it with two different edges. How does it work in sense of the UML structure? We create a test system, but test system in this case is very, very simple. It has only information about units, let's say units in our graph. And we add one more abstract level. It is abstract unit. Abstract unit is superclass to all our abstract and of course non-abstract classes. Now we have two levels of abstraction. This unit has two types of attributes. It's array of clients and array of providers. Actually, type of this unit is the same. The type is the same unit. This is the relationship. Unit has arrays of units. And this class has method execute, which must be overridden in all subclasses. In all subclasses must be implemented method execute. Of course, it is simple model in real system. It could be many different lists of clients, many different lists of providers, but we speak about relatively simple implementation and, of course, example. For simplest case, we don't need both lists of clients and providers. We can have only clients and only providers. In examples which we will discuss in LabVIEW will be only clients, but generally can be both. How to organize such a flexibility? We start our system, we create again light wheels, central processor, helm, combustion engine. But we store them in the array. Or maybe it's not array, maybe it's some more advanced data structure. But references to these units are kept just as units. So after that, we continue working with initialization information, continue reading any file or continue processing read information, and set providers and clients to each unit. Each unit itself knows from where does it get information and where does it send information. So as a result, communications are performed between unit and its subscribers and providers. And all communications are performed at level of the single abstract class unit. Of course, I want to emphasize, this is a simple example. It could be more advanced implementation, but based on the same basic ideas. Now we go to an example. And we forget about cars actually, we don't have car here. Instead we consider flexible program which can do simple mathematical operations. Program which doesn't know much about mathematics, but depending on initialization information, it can do different calculations. The only limitation which I applied for this code, I limited it to unary operations. Unary operations are operations which have one output and one output, like +1, -1, square power in LabVIEW, and so on. And here there are 3 examples. We want a program which will do different calculations dependently on initialization information. Simplest, just show the input dialog and show output dialog, nothing more. The same program would do the same input dialog but +1 to input double value and show the result. And at the bottom we have a more complicated calculation. We have +1 square power, and after that we want the same program to do branching. In one branch it would deduce 1 and take square root and show the result. In second branch it will add 1, take square root and show the result. And we want the same program, the same code to do exactly what is written in any files. UML diagram of such a structure. The test system is replaced by factory. We don't have anything to test, we just need to create structure of our relationships. We have abstract unit which has only clients. We don't need providers, only clients, because it's simple program. And we have abstract method execute. We have 6 specific classes. Show input dialog, input double, show output dialog, class output value, class +1, -1, square, and square root. All of them implement one single step of our calculations. And it doesn't matter how long our calculations, so far as these calculations include only these steps. Now I go to LabVIEW. This is a simple project which implements our calculations. Main VI of this project has very simple code. It reads initialization information, creates objects. After that, second step, it gets one object which is initial source of the information. Of course, in our case, it's input value, and calls execute method of this object. Nothing more. After that, it destroys the whole system of the objects. And this is our code at the top level. As I said, it is very simple top level code. The most interesting, of course, happens in our constructor. I open constructor here and look in its block diagram. We read ini file. Of course, we have to show dialog. Which ini file do we read? Because we have different ini files for different calculations. After that, we take structure of our sections ini file. It will be names of objects. Depending on which class is used, we create different instances of different classes. And for each our 6 classes, there are 6 different cases in our case structure. I show now case for our simplest calculation. First section, first object. The name of object is input. Please don't mistake. In this implementation, it is name of the object. It is not class which is used. Class is given as a key in this section, and class is input value, name of our class. And it has a list of clients. Of course, it is a simplest case. It has only one client, output. Second section is output, which must show us the result, the same value actually. And class is output value, and list of clients has nothing, because it must show us the value, but it must not pass the information to any other object. First we create our first class. It will be input value. Second we create output value. We assemble them as an array. And at second step we continue to work with initialization information, and we assign list of clients for each our member of our network. And this is assignment of list of clients. Let's start our program. I start the program, I get the dialog, and I take the same file which we just considered. The input value we can put, say, 56. Click OK, and we get 56 as the output. Now let's take next ini file. Next ini file would be +1. In this case, input object has the client +1 object. +1 object uses class +1 and has output as its client. So exactly the same procedure will result in the following calculations. We start the same program, but we select next in file. We put the same 56 and we get 57 as the result. Now we have next file. And next file provides us a complicated formula. If we go back to PowerPoint presentation, it is formula at the bottom with branching. Input class sends the value to 1 underline +1. So it's a little bit more complicated naming system because we have many objects here. It uses class +1, takes square root, sends to 2 underline square, and 2 underline square has 2 clients, comma separated here in this case. One 3m minus 1 and second 3p plus 1. Next is the first branch, 3m minus 1, 3m square root, and output minus. The second branch is 3p plus 1, and it has often instances of the same classes, +1, square root, and output value. So as a result, as you see, we reuse the same class several times here, like for example +1, first time, second time, or square root, first time, second time. But we create different instances of this class. Now we try to run the program. Select the init file and let's say put 4 as input. We have one output 4.89 and so, and second output 5.099. It's exactly what we expect. If we want to check it, I did manual calculations for 2 outputs for input 10 and 2 outputs for input 4. Now, the program is actually very interesting and beautiful, but there is one conflict with good programming practice. And good programming practice is when we create new objects, when we create new units, we have to avoid changing of the main code. But when we create a new unit here, every time we have to put one more root in this case structure. It's not a big deal, of course, but when we have a large system with many different types of communications, we have many of such structures, and it could be a limitation. Second example will be dynamic assembling of such class structure. I open next project. This project is almost the same, with the difference that when we open our constructor for the system, we create our classes dynamically. This is dynamic invocation of constructors for our classes. And constructors are a little bit specific here, but we will come to it later. In this case, you can outsource, for example, creation of different units to some other developers who will not have any right to touch main code of the program. They will supply only code of different units. You can spread development between different members of your team, just because there is no direct link between main program and different specific classes. Now, how does it work here? Instead of reading name of the class, which is placed in header of the case structure, we read path to the constructor. As a result, the ini file looks a little bit different. Instead of name here, it is path. Not a big deal here, but still there is some inconvenience in it. So, there is one more option here. And option is, instead of dynamic call for the constructors, we can use factory pattern. And we will speak about it too. Now, in this case, the code is simpler, of course. We get path to the class instead of the class to the constructor. We create our object, we cast it to object of our unit, abstract unit type, and invoke our initialization code. But in this case, constructor is not actually specific. It's really questionable what is constructor. Is this constructor or this is constructor? Limitation is that constructor must generally has no dynamic dispatch terminals. And here constructor must have them. As a result, we have to re-implement, change structure of each constructor in our project. It has to have the same name, it has to have dynamic dispatch terminals, and it has to call constructor of all superclass method call parent instead of direct explicit call to the constructor. In this case, we actually break the system of relationship, default system of the relationship. There is no problem in it, but every time when we change something, we have to keep in mind that standard tools do not work on our constructors. I tried this approach to different kind of models. Of course, it is very easy to implement to native by-value classes of LabVIEW. But if you want to do something with references in these classes, you have to implement reference handling on your own. And of course, you don't do anything unusual in this case. You just implement your code suitable to such kind of factory pattern. In Group 4 and G#, it is possible, but as I said, this easiness of implementation would require special care when you develop your project more, because the errors are very easy to implement. When you create a new class, for example, with tools for Group 4, you create constructor which is not suitable for your implementation. After that, you have to change that. After that, you have to take care that all relations are okay. I tried to do it in Group 3. You could say that who needs Group 3 now, but there are a lot of projects which are still using Group 3. I know even projects which are still using Group 1. LabVIEW programs have very long life sometimes. I didn't succeed to use factory pattern for Group 3, but of course you can challenge me and do it better than I did. Now, What is limitation in this simple example which I provided you in this couple of simple projects for calculations? It is extensive recursion. We call input, call output, and it is a two-step recursion. Not so much. We add +1, and it's already 3 steps. One branch of our advanced calculation. This branch is 6 steps. And this is a very simple example. In practice, we don't want to have flexible architecture, but paid with very solid execution chain, which is actually happen when we use extensive recursion. As a result, in real system, we use asynchronous processes. And asynchronous processes do not call each other or use other means of communications. Sometimes they call, of course, direct methods, and there is nothing wrong to use recursion, but they use, instead of direct call, they often use queues. You represent each direction of communication as queue here. And in this case, when we create structure of our relationships in our initialization file or some other source, we don't assign classes to classes, units to units. Instead of it, we assign structure of queues. Sometimes the channel is not so simple as a queue and channel of communication. And we can, for example, create a special class which contains one or many queues which take care about subscribers and providers. In this case, this is structure of such classes. These classes know from where do they get information and where do they send information. But basic principle is the same. You create structure of relationship when you start the program. And of course, in practical implementation, some signals are sent with queues, some signals are sent with more advanced classes, some signals can be sent with recursion. It solely depends on particular needs for this particular system. Now, there is one very unpleasant conclusion in this presentation. There are no free lunches. Flexibility correlates with complexity of initialization information and, of course, with debugging difficulties. I want to go back to initialization file and take ini file for dynamic assembling of classes, and as you see, it is completely unreadable for very simple case of calculations. So I highly recommend, if you need to do such or certainly more advanced initialization of your system, create user interface which will help assembling such files or help in assembling database for configuration. Many customers will say, no, we can work in Notepad ourselves, we don't want to pay you for this. And after that, they will call you day after day, month after month, why it doesn't work. Now, can we reduce amount of initialization information? In some cases, yes. Look, 2 branches in our formula are the same. We can reuse the same objects. We go back to this file and see, in our case, 2 square object has 2 clients, 3m minus 1, 3p plus 1. 3m minus 1 sends its result to 3m square root, 3p plus 1 to 3p square root. But why don't we use the same branch? It's exactly the same, this and this step, 2 steps. And we can do it, of course. I can show you initialization file for this. It's much shorter. See, client for 3m minus 1 is common square root. And client for 3p plus 1 is common square root, which in turn sends information to output. Simply, these 2 objects will be reduced 2 times. Of course, it's difficult to predict that somebody will need such simple calculations, but sometimes it works. But, as I said, there are no free lunches. I open such a file. I put, let's say, 10 as input. And as output, I have 10.95 and output 11.04. Output 10, output 11. Now, if I start the same file and open full version of initialization information, 10 input, okay, I have output minus 10.95 and output plus 11.045. What is the difference? Difference in titles. Why? Because when I created this output value method, I added name of class to the dialog. And if we reuse our class, we cannot recognize from which branch do we get which value. Of course, it's possible to attach, instead of double value, attach some more information which will show what is source for information, which branch was used, but as was said, there are no free lunches. We save on something, we pay with something else. So I think it is end of this presentation, and I want to thank you everybody who was interested and who was listening, and I hope you will be able to implement these ideas in more advanced, more interesting projects. Thank you.